Here's a number of statements about statistical power. Informally, power's the chance of finding something if it really is there. More formally, power is 1 minus beta, you might say 1 minus beta, the probability of rejecting the null hypothesis if we should. Power is the probability of getting a p-value less than alpha, that is getting statistical significance, if there really is an effect of size delta. For example, delta 0.5, a medium size effect. And we make statements like, for independent groups, if we have two groups of size n equals 30 and choose alpha 05, then the power is 0.48 to find an effect size of 0.5. In other words, just a coin toss chance, a 48% chance of getting statistical significance if there is a true effect of delta 0.5 in the population. We can use power analysis to tell us what n we need to have some desired power, such as 0.8 or 0.9, to find an effect of a particular stated size using our chosen alpha. The trouble is that power analysis depends on NHST and dichotomous decision making. And if that's what you're using, you definitely need to take statistical power seriously. However, there is a better way. Use instead estimation and precision for planning to choose n to achieve your desired target MOE. But now more about power. Here are two power diagrams, just examples. In proper software, you'd be able to calculate power for a much wider variety of values and situations. In the upper panel, we have alpha 0.05, in the lower panel, 0.01, independent groups design. And these curves tell us about the relationship. What power for a particular n and for a particular effect size. So two groups of n equals 30 to find a true effect, medium size effect, delta 0.5, then power is 0.48. We need to know and consider sample size, alpha, true effect size, and power. And these two figures illustrate the relationships amongst those four quantities for the independent group's design. If we have a more stringent criterion for statistical significance, 0.01, then two groups of size 30 and a true effect of 0.5, power is only 0.24, only about half what it was with the 05 criterion. If we want to ask what n do I need to achieve a power of 0.8 using alpha 0.01, then I can come across here, and if I'm looking for an effect size of 0.6, for example, I come across to about there on the curve, that's about 0.8, and drop down. I need two groups of size about n equals 66. If I want to find a true effect of 0.5, then I'm going to need much larger samples, two samples almost of size 100. Again, these figures show how these four quantities trade off and relate. For the paired design, we have comparable figures that show us how for this design, power, sample size, true effect size, and alpha all interrelate, but we need to consider an additional parameter, rho, the population correlation between pre-test and post-test, between the two measures in the paired design. This upper panel is for alpha 0.05, rho 0.6, and down here alpha 05, rho 0.8. Fairly often in practice, rho is around this sort of 0.5, 0.6, 0.8 range of values, but there are no guarantees. And now these figures tell us about the interrelationship of all these quantities, and we can say things like, if we have n equals 30 and use alpha 05 and assume rho is 0.8, then for true effect size of 0.5, we get power of 0.99, a 99% chance of statistical significance if we have n equals 30, alpha 05, and there is this high correlation in the population, then power is 0.99. Power software allows us to find power and study this relationship for a full range of values of all these parameters, and also for designs much more complicated than just independent groups or paired. We should use figures like this not to find what is the correct n to use for our study, but to investigate how these various values interrelate. So we might be saying, well, if I like power of 0.8, then I need n of such and such a size. But I'd really like power of 0.9. How much bigger will it have to be? And then you can weigh up, can you afford to use this larger n in order to get higher power? And certainly high power is good because it gives you a much higher probability of getting statistical significance, all other things being the same. I need to mention post-hoc power, which is indeed a bad idea. It's calculated after data are obtained, and instead of nominating a particular effect size of research interest, we do the calculation using the obtained D from our study. And this, of course, bounces around a lot just through sampling variability if we run the study over and over. And it turns out that post-hoc power really just tells us about D, our result, and very little fundamental about our study. Here's a simulation to illustrate post-hoc power. It's an ESCI page that's not part of ESCI intro. It simulates the results of a 2 independent groups study. The 2 independent groups are of size N1 is 40, N2 is 20, set up with true population effect size of 0.4. So if I click another experiment, I'll get another set of data and I'll calculate from that the obtained D. On this particular case, we happen to get a mean for our test group here, and for our control group, just a tiny bit of difference. This leads to D of 0.06. In fact, there's a true effect size of 0.4 in the population. Let's do it again. And here I happen to get a much larger D, a much larger difference between the two sample means, D of 0.8. So keep an eye on this D down here and see how it bounces round either side of the true population effect size of 0.4. 0.2, 0.3, 0.3, 0.2, 0.1, 0.2, 0.95, 0.55, 0.39, and so on. Now, if I show you post-hoc power, don't use. This is calculated from our particular D. So if I do the study again, I calculated using 0.5 D that the post-hoc power is 0.49. So we could state that the power of this experiment is 0.49 to find a true effect of 0.54, which is quite true, but not very helpful because the true effect is always 0.4, and the calculation that uses just the particular value we got this time round really only tells us about this result, nothing fundamental about the study. So as I run a few more studies, just notice how post-hoc power bounces around, really in parallel with or reflecting the D values. There's one that happens to be higher than the true power of 0.3 because we happen to have got a sample D rather higher than the true population effect size. A bit lower. So a statement of what the post-hoc power is tells us virtually nothing about the underlying study. It just reflects the particular sample Cohen's D value we obtained. Yes, post-hoc power has been devastatingly criticised, basically because it doesn't tell us what we want to know. That's something fundamental about our study. The chance we'll find an effect of a size chosen to be meaningful in our research situation. It merely reflects the outcome of our study. It tells us nothing new. I only mention it because some software, did anyone mention SPSS, may give post-hoc power in its printouts. Simply don't use it. If you see a power value, always ask power to find what particular target delta, what particular chosen true effect size. And unless you can see that clearly stated, then perhaps you've got post-hoc power. It's going to be misleading and of no use. Don't use it. And more generally, thinking of power, well, consider using estimation instead of power and NHST, and using precision for planning instead of power.